Hello, in this video we're going to be talking about the thing that causes waves called oscillations. Anything that moves in this general way will create a wave and is sort of the foundation of all waves. This is topic 4 in the data booklet to kind of follow up on our investigation in class of oscillations. Alright, some things you definitely need to know. There are two really important conditions for this thing called simple harmonic motion to happen. And it's defined by these two conditions. It's a very mathy definition. The IB loves to ask you to define simple harmonic motion. It is always 2 points. You get 2 points for saying these two things. First, it's all about acceleration and displacement and how they relate. First is that the acceleration is proportional to displacement. They depend on each other in a direct proportional way mathematically. And also, the acceleration is always towards equilibrium. In other words, always opposite displacement, and we'll look at that. This would then be the relationship that defines it in math terms. This right here, remember, is a symbol for proportional to, which means if I double the displacement, then the acceleration would double. If I cut the displacement in half, then the acceleration would cut it in half. They scale exactly the same way. The negative sign is a way to show that the directions are always opposite. So if I have a displacement to the left, my acceleration is to the right, and vice versa. So this is the definition of simple harmonic motion. You will definitely be asked about it. HL students will look later. You have an equation that gets a little more detailed than this. Rather than just the proportion, we get the whole equation with like a constant more or less out front. But this version of the equation itself is not in the data booklet. You do need to memorize that this is the definition and it is a math definition. And so what we'll look at in a little bit is that there's a force that causes this acceleration. Whenever I have acceleration, there's a net force. And that force must always be directed towards equilibrium then, so we call it a restoring force. It's always trying to push the thing back to rest position. So simple harmonic motion in a way is the story of this thing always trying to get back to its rest position, and it gets there with so much energy that it keeps going, then it tries to go back, keeps going, tries to go back. All right, here's an example of this idea of a restoring force. Is a spring, and we can imagine a spring that's horizontally like on a table. So this is of course, classic block on the floor moving back and forth. And it's attached to a spring that can both compress and stretch. So here's the rest position where it would just sit naturally. The force is 0. But you can imagine I could stretch this spring. In this case, my displacement is to the right. So I have like a positive displacement probably, and my force is to the left, so I would have a negative force, which means I would also have a negative acceleration, because remember, those two vectors are always in the same direction, since net force equals ma. This would be a restoring force, and it's trying to push the box back towards the rest position, because the spring just wants to chill. But the cruel trick of it is that once the box makes it to equilibrium, it has been accelerated by this force. It's moving pretty quick, and now it's going to overshoot. And it's going to keep going to the left. It's going to get over here. The spring will then compress, and that compression is going to mean there's a spring force to the right. And so we can maybe see what's going to happen here now to this poor box. Now its displacement is to the left. The force is to the right. Again, in opposite directions, always. It's going to get pushed back to equilibrium, now moving to the right. So the fact that this spring force always tries to push towards equilibrium is what's going to make it naturally bounce back and forth forever. Until, of course, we start talking about things like friction and things that will slow it down. But this force always trying to push towards the center, the rest position, is the whole thing that makes simple harmonic motion happen, that makes this vibration happen, and this vibration will eventually perhaps create a wave. The most important graph for this unit then is this one, and it's a weird graph, but it's acceleration versus displacement. And so from our equation and from kind of looking into this with your investigation, we should have seen that the acceleration and displacement are proportional. and there's a negative relationship. We would call this a negative directly proportional relationship. It is proportional because if I double the displacement, the acceleration will double. They depend on each other in a proportional way, and it goes through the origin. Very important graph. The IB almost always has this graph on the exam one way or another. You might have to pick it out of a lineup or draw it yourself. And again, if we read this, it's weird because it's not a versus time graph like we're used to. So it's a different type of graph that we're used to seeing. But it basically is showing me that if the displacement is positive, then the acceleration is negative. And if the displacement is negative, then the acceleration is positive. Acceleration, the best thing to do is think net force. Those two things always point the same way. So if we're talking horizontal, then if my displacement is to the right, then the acceleration and the net force is to the left. And if the displacement is to the left, then the net force is to the right. Or if I'm up, if my displacement is up and vertical, then my acceleration and force will be down, and vice versa. It's always in opposite directions. So this graph is really, really important. Okay, there are a lot of objects and things where this happens. Here are a few examples of simple harmonic motion that we'll look at and perhaps you might study in some detail. But here are a couple different places where simple harmonic motion comes up. The mass on a spring is a classic physics teacher go-to because it is like the simplest system that we can do it for. But there's more relevant everyday life things. Pendulums count. This is another one that we'll see a lot. Something hanging from a string, swaying back and forth. Well, when it's to the left, there's a little bit of gravity that tries to pull it to the right. When it's to the right, there's a little bit of gravity that tries to pull it to the left. So here, gravity is the restoring force. If we really want to get into it, vector components of the force of gravity act as the restoring force and always try and pull this thing back to the center position, which makes it swing back and forth. Speakers are very much springs. The way that they're connected is in a springy kind of way. If you push it down on a speaker cone, it wants to pull back up. And if you pull it up, it wants to pull back down. It always wants to be at rest. So those are used to create sound waves. A buoy in the ocean is another example. Of course, an ocean wave will make it bounce up and down. Or if I push down on the buoy, there will be a force that tries to push it back up because it floats. And then if too much of it gets out of the water, it'll want to come back down because of gravity. So sometimes there's like a buoyant force and a force of gravity that are combining, much like the spring force and gravity do in a mass spring. So a buoy is another example of harmonic motion. And some others, of course, the trampoline is a spring, more or less, that does the same kind of thing. And instrument strings also do the same. When I push it to the left, it wants to go back to the middle. If I push it to the right, it wants to go back to the middle. So they'll vibrate and again create sound waves. So these are all types of vibrations that will happen that will create harmonic motion. And the reason being, in all of these cases, these things more or less all act like springs in a way we can think of it. Better yet, the force is always towards equilibrium. So there's always a thing trying to push all of these things back to their rest position. And that's what makes harmonic motion happen. As an equation for that kind of force, we might remember that there is an equation for the force from a spring called Hooke's law that we can look back at. Do remember this equation is not in the data booklet. It is a really good one to know, though. This is the force from a spring. The force that a spring exerts on an object when it's stretched a certain distance from equilibrium. And the force is negative k times x. Well, that tells us the force depends on negative x. Force is proportional to negative x, which means a spring force will always cause harmonic motion. Harmonic motion happens whenever the acceleration is proportional to negative x. And since acceleration and force are proportional, this will also be true for a spring force. Remember, K is a spring constant. This is something that measures sort of the stiffness of a spring, measured in newtons per meter. It's a certain value for a certain spring, so based on the stretchiness of that spring. Last thing that we'll talk about here is damping. Damping is an effect that in any realistic scenario we see a lot. We see as something bounces back and forth, nothing will really do that forever. If I let a pendulum go back and forth, eventually it'll come to rest. If I let that spring bounce up and down long enough, eventually it'll come to rest. You play a note on a string instrument, eventually that will come to rest. And the reason is because there's always some kind of resistive force, friction or air resistance or whatever, that's going to slow down the motion, steal away the energy over time in the form of heat. And so what we see is that the amplitude, we would say, of this wave decreases over time. The height of the peaks gets shorter and shorter and shorter. This we call damping. We don't really get into the mathematics of damping. You just need to be able to talk about it in a sort of qualitative way. That is, energy is taken away from the system by these resistive forces. The peaks will get lower and lower. And that is pretty much what you need for the intro to oscillations. That should be enough to get you going based on your first few activities. For HL students, we will get into some more exciting mathy stuff based on these equations of waves and how these work in a more mathematical way. But the most important thing is that definition of harmonic motion, acceleration, and displacement, and how they are related. So there you go. Have fun.